So the first half is about representing surfaces. The second part is about using surfaces in the boundary integral method for solving the equations of motion for rather specialized conditions. So sometimes you're lucky and have a nice square grid and square boundaries, and you can fit a square grid in it and things like that. Very often the boundaries are complex and you'd like to represent them. They may be moving, as in water waves, the surface of the water moves. There may be liquid drops in flow where the drops are distorting. You may have phase changes, so there might be evaporation from a surface, so the surface moves, or solidification. So there are cases where the surface moves. I'm not talking about, in this half lecture, about the dynamics of how surfaces move, just how do you represent them. And there are two different, totally different approaches. One is you can mark the surface, so there's some random X's dotted around a surface, saying that I am marking the surface at these points. The alternative is to mark the volume, and if you're on the boundary of the volume is the surface. There are advantages in both. So if you mark the volume, it's rather good if the topology changes. So if your drop splits into two drops, then if you just mark the volume, it happens that liquid is in one drop or the other drop. But as long as you're marking the liquid, the volume, nothing changes, whether it's one drop or broken into two. If you mark the surfaces, and you have one list of points around the surface, and you break the drop into two, you've somehow got to arrange for two lists to exist. It's even worse when you merge them. You have two lists, and you have to merge two lists, and really how you join the lists together is quite complicated. However, marking the surface is much better for if you have surface tension, capillary forces. You can work out the curvature of the surface much better if you've marked the surface compared with marking the volume. Okay, so in 2 dimensions, the surface is a one-dimensional object. It's just a curve, and I'm describing the curve as position in 2 dimensions as a function of a parameter t. Remember, I'm not interested at the moment in how the surface moves, so t is available to be the parameter that changes as I go around the surface. And if I have marked points, which are x subscript I, and then the next point is x subscript I plus 1, I allow the parameter t to change between I and I plus 1 in that little segment of the curve. And then the simplest representation of the surface is just to have straight line segments between the known points. So this is a linear function of t that vanishes at one end. This is a linear function of t that vanishes at the other end. So we have that would be that combination of linear points varies between xi when t is I and is xi plus 1 at t equals I plus 1. Okay, so that's very simple. The big problem is if you wanted to know the curvature when you've got straight line segments, all the curvature is concentrated in a delta function at the jump in slope at the points, which is not too healthy. You can do quadratics between the data points. That's not particularly helpful. Much better is something called a cubic spline. So a cubic spline are cubics, and it's one cubic on one interval and a totally different cubic on the next interval and a different cubic on the next interval. So it's a succession of different cubics, each restricted to an interval, and it goes between xi and xi plus 1. You can see there are 3 cubic expressions. I've switched to tau, which is the difference between t and I. So at the point t equals I, this tau is 0, and at the point t is I plus 1, tau is 1. Okay, so these cubics have been chosen so that all of these cubics vanish at tau equals 0, where this cubic is 1. So x is equal to xi at tau equals 0, and then all of these cubics have been chosen to vanish at tau equal, 1, 2, and that one have been chosen to vanish at tau equals 1, except for this one where this is 1. So we get xi plus 1. And there are two free parameters. A cubic has got 4 parameters. 2 of them are fixed by the positions at the beginning and the end of the interval, and 2 others have been chosen to be, in fact, the derivatives at the beginning and the derivative, there's a dot there, the derivative, in other words, the tangent at the beginning of the interval and the tangent at the end of the interval. I don't know these tangents. I don't know those. But what I now do is I say, please can I have the tangents so that the cubic in this interval is continuous. Well, I automatically get with this expression that the cubic in this interval is continuous with the cubic in this interval, and the derivative at the beginning is equal to the derivative at the end, because I'm using the points and the derivatives. And now I ask that more than at the junction, which technically called the knot, we not only have the function is continuous and the derivative is continuous, but the curvature, the second derivative, is continuous. If I ask the second derivative is continuous, I get a relationship between the unknown derivatives there and the unknown derivatives there. So I get this condition is the derivative, the tangent at I, plus a bit of the tangent at I plus 1 and I minus 1, is related to the values at I plus 1 and I minus 1. So you then have a tridiagonal matrix to solve to find the unknown tangents. But the tridiagonal matrices work quite well. So this cubic is this succession of cubics, called a cubic spline, is actually bringing in information from a long way away. And it gives us a curve which is continuous value, derivative, and second derivative. I rather like a curvature which is continuous when I'm working out surface tension forces. Okay, so now I've got this curve. I can work out the unit tangent, which is just the derivative divided by the size of the derivative. And I can work out the curvature by the second derivatives. I can do other things. As I have got a complete description of the curve, I can work out the arc length along the curve, and then I can choose to move the points, so to distribute them in such a way that they're equiarc spaced length the curve. So I can regrid quite easily in one dimension. And in fact, I don't always make them equally spaced. If I happen to have one drop here and one drop here coming close together, I might say, please put extra concentration of points where they're close, and I have a penalty function that weights the redistribution of points. Very easy in a two-dimensional world. And down here I'm saying splines are a good idea. There are quadratic splines, cubic splines, and quartic splines. Where you tie one spline to another, you always tie it on the data values if they're odd splines, and if they're even polynomials, you tie them at the midpoint for some technical stability reasons. And then there are things called B-splines, and they are compact. In other words, they vanish outside 4 intervals here. So the plus sign means this is 0 if 2 plus x is negative, and it is 2 plus x if 2 plus x is positive. So this cubic switches on at -2, that one switches on at -1. These switch on, and they all end up cancelling beyond 2. Okay, surfaces in 3 dimensions. Well, the obvious thing to do is to have flat triangles You have data points that are on, you've marked the surface with some data points, and you can put between 3 points that you know are on the surface, you could put a flat triangle. There are other possibilities called bicubics over rectangles. There's an interesting idea just slid in here, which I'm not going to say too much about. Splines are very much a one-dimensional idea. You ask, what is the generalization to higher dimensions? And the answer is something called radial basis functions. Does it say that there? Radial basis functions. Now I've said it, I won't say any more. Okay. So on surfaces, you can redistribute points by giving the points a tangential velocity that will move them around the surface. They sort of then slide out of the surface, unfortunately. And you can do tricks like if your surface is deforming and your triangles get distorted, you could think of swapping diagonals to make them nicer triangles. How do you work out the curvature given some data, some points which you know are on the surface? It's actually an interesting question. How many points on the surface do you have to know in order to work out the curvature at one place? And I think it's 5. But I'm not. When I tried to find a simple argument a minute ago, I didn't know what it was. So typically you've got triangles, and you'd like to know, you don't want to know the curvature, you want to know the surface tension forces appropriate to that triangle. So you want to know how much surface tension is pulling in across the boundaries of the triangle. So for that you need a tangent to the surface that's pulling out. Now unfortunately we've got these flat triangles. So what you do is you take the normal to that triangle and the normal to that. So okay, so we've got one triangle here and a triangle there and a triangle there, and if I'm trying to work out the tangent, which is sort of the half angle there. So what I can do is I can quite easily work out the normal to this one and then the normal to this one. So I've got the normal there and I've got the normal there, and I take the average of those two normals, and then if I take the cross product of this edge, I end up with the tangent. Okay, so that's my best estimate of the tangent, which is what that expression is doing. It's taking the vector from A to B, crossed with the average of the normals out of here and out of there, and then summing over all of them. And then I realize that the normal out of here with the sum of those vectors adds up to 0, so I've thrown that term away. Sometimes the way you solve the governing equations, you want to know the surface tension associated with a point, not associated with a triangle. So to find the surface forces pulling away at the point A, you have to find all the triangles that use the vertex, A as a vertex. So I've drawn it here for 5, I think. And then you make what's called a Voronoi construction, which is you take the midpoint and the perpendicular to each. So on this perpendicular, we're in equidistance between there and there. And then you do the same for the next line. You take the perpendicular, and so that's along that line, we're in equidistance from these two vertices. And you go round, and then you find out where they all meet. So we've got this inner pentagon, which are all the points in here are nearer to A than they are to any of the other vertices. And now I'm going to work out what are the surface tension forces pulling across that pentagon. So for this triangle here, the force is pulling in the triangle, because these triangles are meeting at an angle. So the surface tension force is flat here, they're pulling in here and here. Actually it's curved above, but because we're in the middle, the tangent direction is parallel to the flat surface underneath it. And I have to find out what is that length. So that length is half that, is half that length. So this length is half this length times the cotangent of that angle. Right. Now, it's a big test in how good you are in geometry. You can prove that that angle's that angle. Okay. Or is it? No, it's pi by 2 minus it. No, sorry. That angle is that angle. Okay. When it comes, so that's all about marking the surfaces, having points in the surface, and that important calculation of the capillary forces involved. The alternative is to mark the volume, and there are several ways of doing that. One is to have an integrator function, which is normally written as C, and C is equal to 0 in one fluid and 1 in the other fluid, and the boundary is the discontinuous transition between 0 and 1. We're just marking where the fluid is, and then in the time evolution you move the indicator function around with the velocities u. You recognize that's a hyperbolic equation and you shouldn't be doing it. What happens is you get values of c which are bigger than 1 and values of c which are less than 1. There are little spurious oscillations around, and they're called flotsam. And every so often you have to go with a brush and sweep them away. So anything which is oscillating near 1, you declare as 1, and anything is oscillating near 0, you declare as 0. And in the volume of fluid treatment, you can actually treat not fluid 0 and fluid 1, but fluid 0 and 1 together, and you have a density of 0 and 1 together, which is 0, the density of fluid 0 if C is 0, and the density of fluid 1 where it's C1. So actually you put a linear function between density 0 and density 1, similar for the viscosities. And then it's sort of nicely set up to be used on a Cartesian grid, and it's probably the best method of working at moderate Reynolds numbers for two fluid calculations. But you want to know the curvature. So you have to go and find out where the surface is. I just know where C is equal to 0 or 1, and I have to try and find where the boundary is. So here's two ways of reconstructing the surface from knowing that C is 1 and 0. So the first crude method is to say if it's 1 here and 0.95 here, then it's 0.95 up there, so it's 1 here, and just at the top 5% it's 0. Similarly, in this case, it's 1 here and it's 0 up there, so we say that if this is 0.73, it's 73% up is 1, and the last 27% is 0. However, when we come down on this side, we're seeing ones and and a number between 1 and 0. So in this case, we put the boundary vertically. So we can reconstruct a surface. It's jolly discontinuous, and if you wanted to work out the curvature, it's very unhappy. So much more complicated is the piecewise linear construction, which says here the interface must be in this block here. So what I'll do is I'll look in the neighboring points, and I can work out the gradient of C in that direction and the gradient of C in that direction by this, the gradient of C, the gradient of C. So I know the direction of the gradient of C. I know I want 73% of this triangle to be C equals 1. And so I cut a line across, which I put a line across which is perpendicular to the gradient of C and has the right amount on one side. And I can see there's a little gap here. I think on the handout, can you see a gap there? So you can see it is curved, and I've got blue, and I think you've got black and black, so you don't see it so well. Okay, so that's much better representation of the surface. but it's still a bit unhealthy if you wanted to find the curvature. But you don't, you just really need the gradients. So surface tension is really a surface tensor. So it has tension in two directions, and then perpendicular to the surface there's no forces. So this is a stress tensor, but in two dimensions, and 1 minus nn, where n is the normal, gives you the gives you that two-dimensional stress tensor, and you can put that in your three-dimensional governing equation. So we've got the Navier-Stokes equation, and we add the divergence of this tensor. And then it's supposed to be a delta function around where c is a half. Well, you want a numerical version of a delta function that exists where the so something whose integral is 1 and is concentrated around where c is a half. The normal is in the direction of the gradient of c, and it's an averaged value. Because it's so discontinuous, we want to average it. So here I'm saying C is typically on a staggered grid in the middle of a block. And if you want to work out the gradient of C there, what you use is plus 2 there, minus 2 there, minus 1 there, plus 1 there, plus 1 there, and minus 1 there. And then you better divide by 8. So it's not just the derivative in that direction across those points, we're sort of averaging along here to get a more sensible gradient. The hyperbolic equation has trouble propagating discontinuous information where we had an integrator function which was 0 or 1. The diffuse interface method, which is also called the phase field method, allows the function, the indicator, is then the indicator is often called phi, the phase field of the phase field, and it would like to be 0 in one fluid, it would like to be 1 in another fluid, but there's a transition, a smooth transition, not a discontinuous transition in between. And you can make a smooth transition by adding a small amount of diffusion, and then you would get rid of spurious oscillations by this term, which really forces it to go to phi equals 0 or phi equals 1, whichever is nearest. So this term drives it to phi equals 0 or phi equals 1. And the result of that equation is there is a boundary layer thickness, a competition between being driven to 0 or 1 and diffusing away from it. There's a boundary layer of thickness, the square root of epsilon 1, epsilon 2. So we can keep this boundary layer thickness small. And there's a very fast time scale of being driven anywhere, which is a time scale of epsilon 2. And the reason I really hate this method is you need to have a very fine spatial grid to resolve this fine length scale, and you need a very small time step to resolve this process, and then you're resolving this equation, and this equation has got nothing to do with physics. This term here has got no van der Waals forces in if you're trying to merge two surfaces properly. Two surfaces will move if the flow is bringing them together, but all of the real physics of disjoining pressures, van der Waals forces, are not there. Surface tension is about there. There's even another problem. If you put a sphere and solve these equations, no fluid motion, just let the sphere there, the volume will sit there shrinking at a rate epsilon 1 divided by the radius of the sphere. So there are ways of fixing that, but then this is already not physics, and then your fix is even worse, it's not physics. Okay, there's a really good idea in level sets. Level sets are good for lots of problems. Unfortunately, the things that they're good at is when the surface, the velocity of the surface is determined locally by just looking at the surface here. Unfortunately, in fluid mechanics, the velocity of the surface is determined by what is happening to the fluid everywhere. So the big advantage called fast marching is not available in for fluid mechanics, but the one good idea is the indicator function is no longer 0, 1, but is a nice smooth continuous variable from -1 to 1 or from -10 to 10. Typically you set the indicator function up to be the distance from at time equals 0, the initial moment is the distance from the surface. So it smoothly varies as you go through the surface. And then you advect it around. Eventually the contours of phi may get a bit crowded and you want to reset it to be the distance from the surface. But because it's a nice smooth function, the hyperbolic equation, we have smooth methods, second order methods for dealing with smooth data. So we can move it around, we don't get spurious oscillations and nonsense like that. And finding out where phi equals 0, where the boundary is very easy because you've got lots of data either side of it and you can extrapolate and find out very precisely where the boundary is. So this indicator function, which is not discontinuous but smoothly varying, is a fantastic idea. Okay. Yes, you have a question. Good.
Which of these methods is the best way to the correct accurate curvature?
So the person who invented level sets is Sethian, and he visited Cambridge while I was interested in an emulsion. So I had a computer simulation in 3D of 12 viscous drops in a shear flow moving past, deforming as they move past one another, and I could afford 700 triangles to describe one drop. And I asked him how accurate could he get curvature with his level sets with that sort of spatial resolution, which is 700 divided by 4 pi, the square root of, gives you the space size. And he came up with about 5%, which is exactly what I was getting by the method I've described here, of calculating it from the curvatures. And I should say at the same time, these formulas for the curvature of the surface, I found I needed to use them because my first method was not conservative. I was trying to work out the curvature somewhere and applying a surface tension pressure difference equal to the curvature, and that turns out to be a non-conservative system. So I had a spherical drop there with points on, with triangles on it, and the drop was just migrating sideways because the total surface tension force numerically didn't add up to 0. So these methods of working out what is the surface tension across a line, what pulls on one way, pulls on the other way, and so they cancel when you add them all up. So there's no net surface tension force on a finite drop. Okay, boundary integral methods, sometimes called boundary element methods, sometimes called panel methods. So they only work for linear problems like Stokes flow and potential flow, inviscid potential flow. And you want to know the Green's function for solving Laplace's equation. So they're very good for complex geometry. Solving the equation of motion inside a complex geometry, it doesn't have to be rectangular. So it's very good for dynamics of drops, because the drops are going to assume lots of strange shapes. And it's very good, in fact, for free surface problems, is very good for drops because the method just works out the velocity on the surface. And that's all you want to know if you want to see how the surface is deforming. You can work out the velocity at other points, but the method concentrates on working out the velocity only on the surface. Okay, so for potential flow, do Stokes flow right at the end. For potential flow, we have Laplace's equation. The velocity is the gradient of a velocity potential, and the divergence of the velocity field being zero is Laplace's equation. So we have that equation in some volume, and we're either given the value of the potential or the normal gradient of the potential, and n is the outward normal. And we need a thing called the Green's function that satisfies Laplace's equation and is a delta function at some point x equals psi. So the subscript here says take derivatives with respect to x. Psi is just a fixed parameter, a fixed point. And the Green's function doesn't have to satisfy any boundary conditions. Normally it doesn't. In just some very special geometry, if I'm interested in a drop above a plane, I can find an image system underneath, and then I can automatically satisfy the boundary condition. But there are not many geometries where there's an image system, so you normally don't do that. And then there's what's grandly called Green's theorem. It's not much of a theorem, so I call it a Green's identity. It's really the divergence theorem. And it is that this is the divergence of phi times the gradient of g minus the gradient of phi times g. So I can do a divergence theorem to go from a volume integral to the surface, where I can pick up phi, the normal gradient of g, the normal gradient of phi and g. So standard Green's function, Green's identity, or standard divergence theorem, and then in the volume, del squared phi is 0, so that term goes away, and del squared g is a delta function. And now we can evaluate this. It all depends on where this parameter point is. If it's outside the domain, this volume integral will never see this delta function, so the answer is 0. If this parameter point is inside the volume, then this is moderately constant in that region, so we can take it outside, and the integral of a delta function is 1. The interesting case is in between. If the point is on the surface, and we're going to work on the surface, then we get the average of 0 and 1. As long as the surface is smooth, is flat, is locally flat. If the surface is in fact pointed, the corner of a cube, then what you get is a quarter of the solid angle of the vertex. You don't need to know that. So we're going to now take this case where it's on the boundary. So the point psi is on the boundary of a smooth boundary, so we get a half, and we get half what was the left-hand side. And this is an integral equation. You may be given phi on the boundary, in which case, blue phi, your job is to find d phi, but red d phi by the n. And sometimes it's the other way around. You're given red d phi by the n, and you have to find phi. So this is an integral equation, and solving this solves Laplace's equation, finding just what we want just on the boundary. This is really written for what's called the inside problem. If you're dealing with the flow outside an object, then there's a surface at infinity that you have to include in the surface, and you tend to be called boundary conditions of what's happening on the surface at infinity, and you can do the integral for that, and you can then find that you get the potential at infinity. So if you have the outside problem, this equation, you can have it on the finite body plus the contribution from the surface at infinity, which is phi infinity. Right, we need Green's functions. So in 3 dimensions, it's minus 1 upon 4 pi r. And in 2 dimensions, it's 1 upon 2 pi log r. You can do axisymmetric problems rather than, which is a sort of two-dimensional problem, where you have to take the three-dimensional one and then you can integrate it around the axis and you end up with horrible elliptic functions. There are problems with all sorts of equations. Here I've got an integral equation, and one of the problems that you get with equations is there can be eigensolutions. So it happens that if you give me 1 on the boundary everywhere, the answer is d phi by dn equals 0 everywhere. And that's because phi equals 1 everywhere solves the equation, del squared equals 0. So we have this sort of special solution. And so there's an eigenvector 1 everywhere on the boundary, and there's an adjoint eigenvector, which corresponds, by saying del squared phi equals 0, there's no sources in the interior for phi, and therefore nothing can go out of the boundary, so the integral around the boundary of the flux out has to add up to 0. So this is constraint. You have to know about eigensolutions. There's a problem that the integrand is singular. In 3 dimensions is 1 upon r. This is 1 up at the point we have our point fixed on the boundary. As x goes around the boundary, it goes through this point, and g is infinite. We don't actually want to know the value of g, we want to know the integral of g, and this is in 3 dimensions, 1 upon r is integrable, but it's pretty dangerous for numerical calculations. So the Green's function is 1 upon r. Rather worse, the normal gradient is 1 upon r squared. And 1 upon r squared is singular and not integrable in 3 dimensions. But fortunately, I don't want to know the Green's function. I want to know dg by dn. That involves the normal dotted with the distance along the surface. And on a smooth boundary, this is equal to, if it's a flat boundary, the normal, and I've got x is on the boundary, sorry, psi is some point on the boundary, and x is, I'm integrating with respect to x along the boundary. If it's a flat boundary, then x minus psi is perpendicular to the normal. But the surface is curved. And so there's a quadratic curvature times the quadratic. And now when I divide by x minus psi cubed, I find that the normal gradient is the curvature, is a 1 upon r. It looked like it was 1 upon r squared, but it is in fact 1 upon r. But there's a very big warning: your surface better be smooth. So if you think your surface is piecewise linear, you're stuck. Okay, so we have an integral equation. It's a continuous variable. We have to make it into a finite problem for a finite computer. So we have to discretize. So the game is to divide the surface up into panels. In two-dimensional world, the surface is a curve, and we can divide it into segments. They better not be line segments. They better be curved segments. And in 3 dimensions, we can use triangles, but we have to remember we have to think of them as curved triangles when you're doing things. So one, we have to discretize the surface. The next thing is we represent the unknowns, or the knowns, either phi or d phi by dn is known, one is known and one is unknown, as a sum of amplitudes times basis functions. So I've got basis functions capital phi, and I've got basis functions capital D, capital phi. Sorry, they're the amplitudes, capital phi and capital D phi, and there are basis functions which might be piecewise constant. So the basis function might be a constant and then 0 everywhere. It might be a linear variation, come from 0 up to a value and go linearly down. What is rather, if you have piecewise constant If you have constant on each panel, the method is first order accurate. If you have linear variations of the unknowns over a panel, it's delta x squared accurate. And if you use cubic splines, it's fourth order. But you better use these B splines, which vanish at most places and are non-zero at some point. Otherwise, you're into a large calculation. So we divide the surface into panels. We represent the unknowns with a basis functions and amplitudes, and then we satisfy the integral equations. Normally we satisfy them at collocation points. There are particular points we choose, and for piecewise constant panels we choose the midpoint of the panel. For piecewise linear unknowns we choose the ends of the intervals. There are methods that do it by not satisfying the integral equation at points, but satisfying them in some weighted integral sense, but I don't do that. So our discretized integral equation with full variables, if we just discretize that and bring this time onto this side, we have the half phi at the point, and then this is the normal gradient of g, and then we have g and the normal gradient of phi's. This is an amplitude, that is an amplitude. And the matrix elements, that is dg, are the integral of dg by the end, Green's function, normal derivative of the Green's function times a basis function, and the g here is an integral of the Green's function times the basis function. And it's rather nice that it's pretty useful if the basis functions vanish at most points and just have one or two panels, one or two elements where they are non-zero. Then this is a short-range integral. That's why you want the B-splines, because they're zero most places. And we evaluate these, so this is the integral, and we put x equal to xi. So there are cases where this basis function is zero in this region, and therefore the element is not true. Okay, so to evaluate those terms, short-range integrals, many people use Gaussian integration, which gives quite good accuracy. And the clever thing about Gaussian integration is that it avoids the singular point. When you're integrating with respect to x, it avoids the point x equals psi, which is where everything's singular. I always use trapezoidal integration. You always use trapezoidal integral as long as I'm not on the self panel, that is x is not on the panel where psi is, or the one next to it, or the one next to that. But the remote panels, trapezoidal integration is fantastic. The problem with Gaussian, when you have this trick and you use the Gaussian integration on the self panel, that's where integrating with respect to x on the panel where psi is, that is not very accurate. So it's a little exercise for you if you've got a Gaussian integrator, and there is one in MATLAB, I think. Is that true? Try integrating sine from 0 to pi, and with 8 Gaussian points, and you'll get an accuracy of 10 to the minus 15. Try integrating log x, that's our singular integral that we have to integrate, and you get an accuracy of 10 to the minus 2. So I'm telling you, don't do it that way. What you should do is, you know it has a logarithmic integral, a logarithmic singularity, and you know the amplitude. And so what you do is you say the Green's function is the singular bit in a very simple form, plus a regular amount term, or the remainder, and I can integrate that by hand with respect to x. And the answer is, integrating with respect to x is log delta of the ends. So I can integrate that one analytically. This is a regular, nice function, so I can integrate that by a trapezoidal rule. And I do it not only on the self panel, where the singularity is, but I do it on the adjacent one and the second adjacent one. I've even sometimes done it all the way around. There's an eigen solution. When we try to solve this equation for given coefficients the phi's to find out the phi amplitudes. So given d phi by dn on the boundary, find phi on the boundary, there is an eigensolution that I showed before, phi equals 1, associated with d phi by dn equals 0 everywhere. How do you avoid the eigensolution? So the official thing is you have to live in the space that's orthogonal to the eigenfunction. But you don't do that. So one thing is, my very bad research student just relied on the fact that he didn't get these matrix elements very accurately, so it wasn't quite singular, and then he inverted, and it's nearly worked. Don't do that. So my trick is, if you've got a matrix A which is singular, for the eigenvector E and the adjoint eigenvector, that deals with non-symmetric matrices, so you can change the eigenvalue B for this for this eigenvector, the eigenvalue of A is 0. So why don't you change it to alpha? So if you add that to this matrix, the eigenvalue for the eigenvector E has become alpha. Alpha 3 is a good number. And you haven't upset any of the other directions. So that's a good thing to do. And then for the interior problem, this is what the eigenvectors are. Okay, so you have a code. It's very complicated. You better test it. And the good thing is, in 2 dimensions, it's very easy because phi is r to the k cos k theta is a solution of Laplace's equation. I can work out the normal derivative quite easily because I can differentiate with respect to r, I can differentiate with respect to theta, so it's the normal component, the radial component of the normal and the theta component of the normal times the d phi by the r, d phi by the theta. So I can feed this into my integral equation and see if I get that out. I can feed that in and see if I get that out. And I can test how accurate they are. So we have to discuss costs. So firstly, there's a human cost. It is a very big effort to write this code and get it right. So there's that. Many people say the boundary integral method is faster than solving the equation in the interior because there are less points on the surface than there are in the interior. And that's not quite right. So here's the calculation. Suppose we're in 2 dimensions and we have an n by n grid. There are n squared points in the interior. There are 4n points around the boundary. Now, while there's n squared points there in 2 dimensions, if it's a nice square geometry, there are fast Poisson solvers which will require n log n steps, and so the number of calculations I have to do is the number of points times the number of iterations, and that's n cubed log n. For the boundary integral method, I have 4n points, so I have a matrix which is 4n times 4n. Unfortunately, that matrix is dense. There's not a fast solver, so I have to have a full solver whose cost is 1/3 the size of the matrix cubed, and so the cost is 11n cubed. So 11n cubed is about the same as n cubed log n. When it goes to 3 dimensions, the comparison is worse. It's n to the 4th log n to do the calculation in the volume. To do the calculation on the surface, it's 72n6, 6 rather than 4. So it's not quite so good. There are big advantages of the boundary integral method. One is this high cost is if you have to do a direct matrix inversion. When you're time stepping, the previous time steps a rather good approximation to the solution at the next time step. And so you could use that previous time step and just make one iteration of your integral equation. And that cuts it down from an n cubed to an n squared calculation. Also, if you're in an infinite geometry, suppose I want to see how a drop oscillates in an infinite fluid, if I do the calculation in the volume of the fluid, how far away is infinity? So I may have a drop at x equals 1, but then I may have to go to x equals 10, which has suddenly increased the volume calculation if I want infinity to go away. And then finally, these fast Poisson methods only exist in nice square geometries. So we're interested in complicated, when a drop breaks into two and forms a little satellite, third drop in between. This is very complicated geometry, and the boundary integral method, which just concentrates on the surface, is a fantastic method. So for getting into complex geometries, the boundary integral is good. How you tackle this dense matrix for the surface, the boundary integral method, there are things called fast multipoles, which I'll describe next lecture, which I've never used them for good reason. Okay, so I sold this method for being used for potential flow and Stokes flow, so there are two transparencies here. How do you do it? How do you solve potential flow? So you start potential flow knowing the surface and knowing the potential on the surface. That's why I'm saying I know at the beginning of the time step where the surface is and what the potential is on the surface. I use my boundary integral technique, feed it the potential on the surface. The boundary integral technique will tell me phi by dn. Because I know phi on the surface, I can work out the tangential derivative of phi. So with the tangential derivative and the normal derivative, I've got the derivative. So I've got the velocity field. So I can therefore move the points on the surface to find the surface at the next time step. Now I have to time step the potential, and the equation from Bernoulli is phi by dt is equal to things like gravity, surface tension, atmospheric pressure, and there's a half grad phi squared, and if you thought quickly, you'd think I've got the wrong sign here, because it's phi by dt plus half grad phi squared, and I've got on the other side. However, I don't want to know phi by dt at a fixed space position. I've got a moving space position where we write it as phi by dt, and the difference between those two is a half grad phi squared. So I've got the correct sign here. Okay. So this time steps phi on the boundary, and you just continue. There are problems, if I have surface tension, that there are capillary waves. And to resolve capillary waves, as you have to, delta t has to be less than delta x to the 3/2 times the surface. If you have capillary waves, you're into one of these energy conserving. This is no dissipation, kinetic energy only. I add potential energy of capillary waves. I have an energy conserving system. This means if numerically I excite some little shortwave capillary waves, I've got them forever. And they'll swamp the solution. So you need some method of getting rid of this numerical noise of propagating capillary waves. One way is to put some smoothing in, which isn't too good. Another way is to do a Fourier transform of phi along the boundary and throw away the high harmonics. Stokes flow. Stokes flow is a sort of potential flow with the vectors rather than scalars. And there is a Green's function called the Stokeslet, and there's the derivative of the streams function, which is called in the low Reynolds number literature the Stresslet. So this is what they are. And you're typically involved in flows where of a drop where there's a viscosity inside and a viscosity outside, and we do a trick. Sorry, I should better explain. The velocity on the boundary, the half comes from evaluating the boundary integral on the boundary, is the Green's function times the forces on the boundary, the surface stress on the boundary, and the gradient of the Green's function times the velocity on the boundary. Right. I typically don't know the stress on the boundary. When I have this one viscous drop when I have a viscous drop with one viscosity inside and one viscosity outside, what I can do is to subtract the equation for the outside flow with the half, and work on the boundary, from the equation on the inside. I end up taking the difference between the stress on the inside and the stress on the outside, which is the capillary pressure jump. So I can turn this equation into half the velocity on the boundary is the jump in the stress is equal to the velocity on the boundary. And I've done a lot of that over the years. There are eigensolutions. If you're studying the internal problem only, rigid body motion is permitted. That doesn't create any stresses as far as the inside is concerned. So translation and rotation rigidly. And also pressure equals 1 doesn't generate any flow in an incompressible fluid. So there are 7 eigensolutions you have to tamper with.